All right, I just started recording, so let's get started. Before our lecture begins, I actually invited a graduate student of mine who is leading the student group that I was mentioning last time so that he can uh, give some information about the UC Davis Energy Club. So Jake, you want to take it away?
Yeah, can you guys all hear me? Okay. I'll keep it real short. My name is Jake Heileman. I'm one of Alan's graduate students. I'm a master's student in the energy graduate group, and some of my colleagues and I have started in the fall a chapter of a global nonprofit called Student Energy. And I posted some info in the chat. But basically, Student Energy, there's chapters all around the world, and we're currently the only chapter in the US. And basically, the goal of our chapter is to bring together mostly grad students and also undergrads to talk about the way that energy issues affect the fight for climate change, the fight against climate change. And so we mostly have like in the fall and winter, we had like meetings every other week where we would have guest speakers and discuss a different topic. Whether it was, we've had people from the grid operator, CAISO, come and talk to us. Some professors or sometimes grad students will give a presentation. This term we're obviously not meeting in person, but I just wanted to reach out in case anyone's looking to learn more about kind of California energy topics and how they relate to climate change. We're going to be having weekly discussion meetings over Zoom and probably on Tuesday evenings. So if anyone's interested in kind of like getting more into learning more about energy stuff as it relates to climate, we're going to be covering some different topics, including transportation, agriculture, and like national energy politics. So there's a link for a sign up if you want to join the email list, and my email's on there as well. And you can also check out the global organization Student Energy at the link in the chat as well. So let me know if anyone has any, if you guys have questions, feel free to put them in the chat or email me at jbheileman. So yeah, we'd love to see some of you on these Zoom meetings, and it's a good way to learn some cool shit while you're quarantining. All right, thanks, Alan.
Yep, thanks, Jake. Great. Okay, yeah, so definitely reach out to him if you're interested. It's a pretty new organization, and so hopefully they'll be spinning up and doing a lot of cool stuff soon. Okay, so lecture 2, we'll start off, and we're going to be talking about energy conversion and efficiency today. Before I dive into those topics, I wanted to quickly finish up our discussion last time about climate change. Okay, let's go. So we were talking about CO2 emissions and thinking about some of the different metrics of impacts. So temperature for both surface, also there's ocean acidification, also the sea level rise and ice caps coverage every year as seasonally the changes and how large the coverage of the ice cap region is. So those are some of the prime metrics with which we're sort of saying that climate change is happening. And that's all happening in the context of a lot of the increase in anthropogenic carbon emissions. And so this is a breakdown of those carbon emissions by country over time for the last couple of years. Okay, whoever is doing the annotation, it's actually showing up for everyone, so let's not do that. Okay, moving on. Yeah, I'll try and figure out if there's a way to make it so that only the host can do the annotation. So this is analysis of emissions data. Actually, more recently, it's been sort of flattening, but that actually has more to do with local economic effects. And since 2016, actually emissions have started to increase a little bit again. So global CO2 actually does continue to rise. And one of the things that we want to think about is how CO2 emissions may continue to change into the future so that we're able to correctly predict effects on the climate. And one of the bodies, or one of the most significant bodies that helps with understanding this research, particularly with climate change, some of you may have heard of, is the Intergovernmental Panel on Climate Change, IPCC. So they're actually a body from the UN that is supposed to look at specific scientific-based information on climate change. And this includes both natural changes, but also anthropogenic, thinking about the political economy, what the risks are associated with climate change, and how we might respond to those. It was established 31 years ago by the UN and convenes thousands and thousands of scientists and experts to contribute purely actually on a voluntary basis. And we have contributors across many, many countries. The major groups of the IPCC are divided into these three working groups, WG 1, 2, and 3. So 1 is thinking about the science of the climate system. And so this is sort of modelers who are figuring out, if I have, this much emissions, then how will the global climate system react? How will climate change over time? Number 2 is looking at natural systems of climate change and consequences. And so these guys are assessing a lot of the impacts of climate change on natural ecosystems as well as on human societies. And then the last working group are scientists who are looking at how you can curb emissions and do climate change mitigation. So thinking about new technologies and thinking about how those technologies like renewables, like electric vehicles, how we can integrate that and how that may change our forecast for emissions. And so together, these three groups help to constitute a lot of the impact assessments that are coming out of the IPCC. The assessment reports are very comprehensive across all the three working groups. They cover basically all the topics that you need to know about climate change. The first assessment report, FAR, was published in 1990. And since then, every 5 or 6 years, they come out with a new assessment report. One of the more famous ones was AR4 back in 2007, and actually it was jointly awarded the Nobel Peace Prize, and so everyone who worked on that report was actually awarded the Nobel Prize. The most recent one was AR5, which was released in 2013, 2014, and the next one is scheduled to be released in 2022. And currently, there are a lot of efforts underway to work on that. And actually, I'm going to be an author on that, which is pretty exciting. And we're working on the transportation sector report chapters in the report. And there's a fairly large team of maybe around 20 or 30 people on that chapter. So we anticipate that'll be released in maybe 1 or 2 years. Okay, so IPCC scenarios, thinking about what are the future of what is the future of CO2 emissions going to look like, and so they consider a whole range of scenarios because there are many sort of different possibilities in terms of how society may try and change their climate mitigation efforts. And so these RCP scenarios are basically temperature scenarios. So RCP 8.5 versus 6 versus 4.5 versus 2.6. That's a scenario in which IPCC thinks that global warming will increase by 8.5 degrees. And so the annual emissions in terms of CO2 that would need to happen for RCP 8.5, for example, is 100 gigatons of CO2 per year. And that will lead to probably the worst climate change. And then for RCP 2.6, right, which is the most optimistic version, you basically reduce anthropogenic CO2 emissions down to 0. So even if we do that, even if we reduce all emissions down to 0, we'll still see an increase in emissions or increase in global temperature by 2.6 degrees. Okay, and so why is that? Why is it that when you reduce CO2, you still see global temperatures going up? Oh yeah. RCP, sorry. RCP stands for representative concentration pathways. Yeah, and so RCP is, so in the 2.6, you are going to get, you are still seeing temperature rise due to the fact that the current CO2 emissions are going to still last for 100 years. So CO2 will stay in the atmosphere and lead to global warming, and the radiative forcing from the CO2 in the atmosphere is still leading to what we're emitting today, is still leading to global warming. Oh, I see. Sorry, I see a comment in the group chat. Yeah. Okay. Sorry. I had a slight mix-up. The number, yeah, that's right, refers to radiative forcing. That is an increase in the, if you remember from the chart from last class, the watts per meter squared of sunlight going into the atmosphere, the stuff that gets trapped inside is going to increase by a certain amount, leading to a different temperature increase. So these numbers aren't actually referring to the actual temperatures. They're referring to increase in the watts per meter squared. So thank you for that correction. Okay, so in terms of the cumulative anthropogenic CO2 of the CO2, leading to what we expect the induced warming potential is relative to our initial baseline in the 1800s. And so you're looking at anywhere on the order of 1 all the way up to 5 degrees Celsius. And so the RCP 8.5, you're going to be talking about ranges in sort of the 4 degrees Celsius territory. Currently, I believe last year, or at the end of last year, if I'm recalling correctly, we reached about 450 ppm for CO2. So we're sort of on this scale right now. And we expect that the cumulative anthropogenic CO2 emissions, right, which is the total amount that's getting emitted and staying in the atmosphere, is going to continue to increase, right? Even if we continue to decrease our CO2, you can think of it as there's this sort of bathtub analogy where the water is sort of filling up, and there's sort of a small drain at the bottom. And even if you decrease the water going in, you still have some CO2 that lingers in the atmosphere for about a century before you get the full drainage from that bathtub. Okay, and so projections of 3 key climate change indicators. You have your surface temperature change, our sea ice extent, and sea level rise. So these are the things that we were talking about last time, except that those were showing historical values, and now these are showing projections across the IPCC RCP scenarios. And you can see here that the changes are fairly drastic depending on which of the scenarios we're looking at, right? And so their average surface temperature change for the RCP 8.5 is in the range of 4 degrees Celsius, as someone had pointed out in chat. And you'll see the sea ice extent will decrease fairly significantly for that same scenario, going down actually to 0 by the time we're in the late 2000s. And you're going to have inevitable sea level rise between 0.5 meter up to about 0.8 meters. And that range is happening sort of even in the most optimistic scenario. So unfortunately, that means that, you know, by the time we get to 2060, 2080, 2100, even in the best scenarios, we are observing sort of a fairly different climate in that world compared to today and compared to a couple centuries ago. Again, this is a more sort of spatial example of those projections, looking at RCP scenarios 2.6 and 8.5, and what the temperature differences are going to look like. So I should note that when we talk about global warming and we think about climate change in terms of just like an increase in average temperature, as I'm sure many of you guys know, that's not sort of the only effect, right? So changes in climate that are so drastic also lead to large changes in extreme events that may lead to, for example, more frequent wildfires, more devastating hurricanes. It's been sort of well established that extreme weather events get worse as a result of climate change, even if we can't attribute like one specific extreme event to climate change itself, on average, those events are going to get worse. And then we can see also change in precipitation is one of the factors. This is the sort of stuff that Working Group 1 of IPCC is going to put out. Yeah, and so if folks are interested in it, the assessment reports are made open and public, and so you can take a look at the IPCC AR5, which is the most recent one, as I had mentioned, and that gives a pretty nice summary. Even it's sort of designed, both sort of for a scientific audience, but also for the general public. There are lots of portions of it that help lay out some of the impacts and findings of the report in sort of a really digestible manner. So definitely take a look if you're interested. Now, thinking about the relation of those climate change impacts and the ways we might mitigate some of those impacts on how it affects our energy system, part of what Working Group 3 does is to think about how the system may change in order to meet specific climate goals. And so the RCP 6 and RCP 2.6, for example, you can see how different the systems look in terms of providing some of these primary energy consumption between these two scenarios. These are produced with what are called these integrated assessment models, which are these really large-scale system models that span many different sectors, and so they'll try to take into account, not only how technology changes, but also how people may change their behavior, how efficiency measures might be implemented, and you can see here that there's actually a pretty stark difference in the sort of technology that needs to be adopted to reach one goal versus another. For example, you'll see that there is significantly less coal in the RCP 2.6 compared to the 6, and they have a lot more nuclear power in that scenario compared to the RCP 6 scenario. And so and also notice that the axes themselves are pretty different. There's this goes up to 1800, this goes up to 1500, which means that the overall energy demand is lower, and so they're getting people to consume less energy, and or the technologies themselves for end use are also becoming more efficient. And so we're not going to get into the guts of how this sort of modeling happens, but we will talk about more sort of qualitatively how we get to directions where you can meet specific types of goals. Okay, so that was sort of a wrap up for lecture 1, and hopefully provides some again motivation about how serious the climate change problem is and how difficult it is for us to meet those goals, but that there is potential and hope for us to do that. Okay, so taking a step back, we're going to think about basics of energy again, sort of going back to our building blocks. Last time we talked about different units and forms of energy and gave a sense of the magnitude of energy and power demand. And so today we'll talk a little bit more formally about what those things actually are, how they're measured, and some examples of getting familiar with energy conversion and the math of thinking about efficiencies as we do energy conversion. Okay, so what is energy? Energy is the ability to do work, right? And so this is The formal sort of physics definition is for force acting through a distance, so it's multiplying amount of force by distance. We measure this, we measure force in terms of newtons, and the SI sort of derivation of the unit, of the Newton unit, is kilograms times meters per second squared. So it's essentially the force required to accelerate 1 kilogram at 1 meter per second squared. And in terms of energy, you are multiplying force by distance, right? Which is what we see up here. And so that's just Newton times distance, and that's how we, that is the derivation of the joule unit that we were talking about in last class. Similarly, right, power, which we also covered, is the rate of energy production. Unit of power is in watts, which is 1 joule per second, right? Or, you know, the force times the distance divided by time. Watts can be used to measure thermal, electrical, or mechanical power. Okay, so energy itself has many different forms. And if you've taken physics class or chemistry, you should be familiar with some of these. And so hopefully this will be mainly just a refresher. So kinetic energy is energy of moving objects, energy of motion. So if you have an object of mass m that's moving at a certain velocity, then we are able to measure its energy as 1/2 its mass times its velocity squared. Potential energy is a different type of energy based off of its gravitational potential. And so energy of position of a mass in a gravitational field. Basically, if I lift an object off the ground, it's gonna have some inherent energy with it because it has the gravitational potential to move, right? To exert a force. So for mass m raised at a distance h off the surface of the Earth, it has potential energy m mass times the gravitational constant times its height. And the gravitational constant on Earth is approximately 9.8 meters per second squared. There's also a couple different other forms of energy. We can think about chemical energy, and this is mainly energy in fuels. Okay, and so when we think about in atoms, right, electrons have configurations, and when they undergo chemical reactions, there is a change in energy. You can have exothermic reactions which produce energy, or endothermic reactions which require energy to be put in for the chemical change to occur. And so up here, here's an example of combustion, and that's the combination of propane and oxygen. It requires some input energy of heat to raise up the temperature, and the combustion will lead to a change in the chemical form to carbon dioxide and water, as well as heat and light, which is what we consider as the change in energy. Nuclear energy, similarly at the atomic level. So this is binding energy of nuclear forces between protons and neutrons. So if you are splitting nuclei, then you get nuclear fission. And so you can see that happening here. If you have a neutron hitting the uranium, it'll split into barium and krypton and release more neutrons. And there's a tremendous release of energy associated with that. And with nuclear fusion, you're taking, so this is an example of isotopes of hydrogen, deuterium, and tritium. where you combine them to form helium, and excess neutron also results in a large energy output. So I would tend to think of chemical energy as sort of energy coming from the manipulation of molecules into different structures, and nuclear energy as the manipulation of atoms into different atoms, and both of those are associated with sort of large energy changes. You also have electromagnetic energy, radiation due to acceleration of charged particles. On the one hand, we're not going to get too much into the formal, physics of electromagnetic energy. On the other hand, actually, a lot of the energy that we're talking about is sort of in this form, right? So when we think about electricity, that energy has to do with this radiation of the charged particles, and so when we are doing measurements of energy associated in electrical form, this is the form of the energy that is taking place. And then lastly, you have thermal energy, which is the sort of movement of atoms and molecules, the average kinetic energy of atoms and molecules. So we can think of temperature and heat as related to this, where thermal energy is being transferred from one set of molecules to another, from one body to another, and you're always sort of moving or you're typically moving from high temperature to low temperature. And we'll talk a little bit more down the line about how these different sorts of forms of energy are more or less useful for the types of applications that we as humans use. So the total amount of energy across the system is basically the sum of all these things. So if you add up your kinetic potential, the internal energy, which is the thermal energy, chemical energy, nuclear energy, and electrical energy, that gives you sort of the full amount of energy of the system. Heat and work. A system and its environment interact via heat and work, and we'll actually look at some nice examples of this once we get to some of the internal combustion engine or any of the fossil fuel combustion technologies. And basically, what we're talking about is having an environment where some force is being exerted, and you are displacing something, and so you can measure this, the force in this particular example of pressure times area, and the change in work as here this might be something like a cylinder where you might be doing combustion as pressure times the change in volume. And so the types of systems that are doing this type of work are usually associated with combustion. And so we're going to do a quick sort of focus aside looking at chemical energy, and the main way we take advantage of that as humans is through combustion. So the combustion of a hydrocarbon fuel, which is a molecule that is mainly built of hydrocarbons, so carbon and hydrogen, looks something like this. You have an N number of carbon molecules, H number of hydrogen molecules. When you combust it with oxygen, it leads to CO2 and H2O. And so when we think about fossil fuels, and even biofuels, they are almost all some form of this hydrocarbon, where you have methane, which is the smallest one, that's natural gas. That's just CH4, and you can increase the number of hydrocarbons, and those are sort of different types of fuels. So ethanol is considered a type of hydrocarbon. You can go up to gasoline, up to diesel, and then as you get longer and longer hydrocarbon chains, you're getting to solids like fats and waxes and that sort of thing. When you combust it, you make a flame that looks like this. And depending on the number of oxygen molecules in the fuel mixture, then you can actually have a different air to fuel ratio, which we denote as AF. So when you have more oxygen, you get what's called a lean fuel air mixture, and you have better and more complete combustion. And that looks like this. Okay, I see a question here. So how will it be different if you have incomplete combustion? Yeah, and so what ends up happening is if you have less oxygen, you have something called a rich fuel air mixture, and that leads to incomplete combustion. And that example looks something more like on the right. So what's happening in incomplete combustion? You get a whole lot of other byproducts, which is why the flame looks different. Some of those byproducts actually include the fuel itself that is uncombusted. So say you had incomplete combustion of gasoline or diesel. This is actually an example that I'm showing in this picture called coal rolling, where people can actually modify the engine of their vehicle to run rich on fuel, and it leads to something like this. A lot of that soot and black particulate matter includes some of that incomplete combustion. So there's going to be uncombusted diesel in here. But also there are other byproducts that are forming as a result of the high fuel mixture, as well as the sort of non-optimal temperature of combustion. And you get the byproducts like more particulate matter. You can get things like NOx and SOx for hydrocarbons that contain impurities such as nitrogen and sulfur. You can get a lot of carbon monoxide. And all of these things will result in this sort of dirty form of emissions. Yeah, and so that's typically what you're going to see with more of these sort of orange type flames, is that you're going to get some byproducts that are leading to that particular color. Okay, so going back to energy forms, we had briefly mentioned this last time. So I think primary energy, secondary, final, and delivered energy. So primary energy are the naturally occurring resources. Secondary energy are resources that are processed. And then the final and delivered energy are those that are being used to provide the final energy services. And so those get converted from our useful energy to meet energy services. Again, heating, cooling, lighting, passenger travel, turning on your TV, turning on your computer. All of these things are sort of the useful energy that we're consuming. And everything between primary energy and that useful energy are intermediate steps. When we think about the quantification of primary energy, secondary energy, final energy, that's where things get kind of interesting. We talked in sort of in theory what the primary energy levels should be, but there needs to be a sort of further discussion about how you actually measure those values. So the first one that I'll introduce you guys to is called heating value. So this is the heat of combustion of fuel. So this is most commonly used for measuring, the primary energy or energy associated with fossil fuels. So this is measured by looking at the amount of heat released during the combustion of a fuel. So I can take a very specific amount of fuel, I can combust it, and figure out its heating value to go back and calculate the primary energy associated with that fuel. There is a heating value specific to each fuel because the properties of combustion, right, the amount of heat that like gasoline versus diesel versus natural gas release for a specified amount of the fuel is going to be different. The heating value is an upper bound of the potential heat that you're able to capture. But remember, there's no sort of system that's able to perfectly capture all that heat. And so this is sort of like the theoretical limit of energy associated with combustion, but that you're never able to get all of that energy. There are two types of heating values that are commonly used today to measure energy content. You have a lower heating value and a higher heating value, so LHV and HHV. And that assumes a particular property of the way in which you are able to use the energy and capture the energy. So in a lower heating value, it assumes that the fuel is combusted, and then the water that comes out of the combustion equation is simply sort of emitted as a gas. A higher heating value is the same thing, but the main difference is that water that is coming out of the chemical reaction of combustion is at a higher temperature. And so there's some latent heat in the water that in theory you could recover. So it's basically saying, like, if we took the energy from combustion and it emits the water, we can collect that temperature difference back down to the initial starting point temperature and say that that is the energy associated with the combustion process. So two different ways of measuring it that result in different numbers, and it's not necessarily that one is correct or versus the other, but it's making an assumption of essentially what sorts of energy can be collected from the actual combustion process. Generally speaking, the higher the content of hydrogen in the fuel, then the higher the heating value. And in fact, hydrogen, the gas itself, has the highest heat value per kilogram of any fuel. And the lower heating value and the higher heating value for something like hydrogen is going to be slightly different, right? So the differences between your LHV and your HHV are also dependent on the fuel. They're not all going to be the same. Yes, so I see a question. So the latent heat of value increases the heating value or reduces the heating value. Well, it's gonna increase it, right? Because essentially what you're saying in a higher heating value is that I can collect more energy because I'm collecting the energy associated with the water cooling down. And that's actually why we call it lower and higher. So the lower is kind of like a lower bound estimate, and the higher is sort of a higher estimate. Okay, I see another question. Higher heating value is good for a fuel source. Well, it's not that either of these things are good or bad, right? These are ways we measure something, and there's a difference in essentially the way that we're doing the measurement. Um, and so actually, if I'll let me jump ahead 2 slides real quick. I'll go back. Um, this is a chart of lower heating value versus higher heating value. Um, and so again, this is a way of doing sort of accounting. So natural gas, you'll see the BTUs per cubic foot is 983 for its lower heating value, and about 1,089 BTUs per cubic foot for its higher heating value. Um, and it's the same natural gas, right? If I combust it one way, there isn't like a natural gas that has a lower heating value and a natural gas that has a higher heating value. They're both the same. They're different ways of measuring, and you are essentially making an assumption when you report LHV versus HHV. But it's nothing different about the actual physical property of the fuel. So I'm going to go back 1 slide. So comparing heating values. So LHV is known as the net calorific value. So to be a little bit more specific, it's the way that the procedure for measuring lower heating value happens is you take some quantity of fuel that starts at 25 degrees Celsius. You combust it, and then you measure sort of the heat output after you return the temperature of the products to 150 degrees Celsius. So this does not include latent heat of vaporizing the water. Whereas the higher heating value, it's the same thing, except you return everything to the initial starting point, 25 degrees Celsius, and that does include the heat of vaporization of the water. Okay, and so you might ask, like, why is it that you do both LHV and HHV? Why not just sort of pick one? Well, depending on sort of the process that you're doing, you may or may not be able to capture energy associated with the latent heat of vaporization. Yeah. One second. I'll get to that question. And so if you choose a specific process, it's not going to account for either the vaporization or not including it. And so we're not going to get so detailed where I think that you're going to need to take this into account all the time, but it's an important assumption because it changes the numbers. And so as you do any process that includes sort of primary heating values for fossil fuels, you should be really clear in saying that you're assuming LHV or HHV. Yeah, okay, so there's a question here. Both LHV and HHV are theoretical upper limits that don't account for inefficiency. Yeah, and so that's right. So let's see, if you were to actually were able to measure sort of the difference in energy states between the pre-combusted molecules and the post-combusted molecules, that like delta energy is going to be slightly different from these, right? Because there are some inefficiencies. You're capturing like a real world like combustion process, and you're measuring that with like real instruments, and you're never going to get like a perfect combustion and a perfect capture of heat and energy associated with that combustion. It's the best that it's kind of like the best we can measure it. And so it's not going to be the theoretical sort of total upper limit. You in theory, you're probably able to get uh, um, a little more energy out than what the LHV and HHV are telling you, but um, in practice, it's not so big of a deal, because what you're getting out of the LHV and HHV is essentially a measurement that's going to be a higher energy value than anything you could capture anyways through any particular technology that takes advantage of combustion of fossil fuels. It's a way of measuring an approximate energy content to figure out what the relative efficiency of a particular process is, right? So we're going to see this in a little bit, but we do combustion of a fossil fuel in order to get like electricity, or in order to get like our car to move, right? And so we're able to measure the electricity coming out of the process that starts with combustion, and the energy, there's some energy that's associated with that electricity. And if we measure that compared to the energy of the primary fuel content, then you can see how much losses there are, right? And so if we're a little bit inaccurate with the LHV and HHV, that's okay, because you want to be kind of in the right ballpark. And when I say sort of in the right ballpark, these values, even though they're not in theory the exact amount of energy, they're going to be pretty close, right? The instrumentation and measurement ability of scientists and the technology they use to capture these values are pretty darn accurate. Okay, and so there, again, these are just some examples for your reference for LHV and HHV values, and they're given in sort of different units, so that you don't have to convert them yourself. So megajoules per kilogram, BTUs per pound, BTUs per cubic foot, as well as down here for liquid fuels, they give it by gallons instead of cubic feet for the volume. As I was mentioning, the difference between the LHV and the HHV is going to depend on the fuel. And you can see on natural gas versus crude oil versus coal versus hydrogen, the differences are fairly wide. And as mentioned, the more hydrogen that you have proportional in the fuel, the larger the difference is going to be as well. Also recall that, again, these values are measured, right, via instruments, and as the accuracy of these instruments changes over time, and also in sort of different conditions and in different regions, you actually do see variation in measurements of heating values for different types of fossil fuels. And so this is a little chart of how the heat content, for example, has changed over time, has decreased since the 1950s. And that can also, it's not only that, there's also some differences in the composition of the fuel. So not so much for like natural gas, which is just methane, but for crude oil, right, you might have slightly more shorter hydrocarbons versus longer hydrocarbons. And so that will lead to some slight differences in your lower heating value and higher heating value as well. Okay, and so because of that, it'll be important that if you're doing any work with, looking at energy content of fossil fuels, that you should mention your source in addition to the fact that you're using LHV or HHV. Okay, So that's a way that we measure primary energy content for fossil fuels. But what about for energy content of non-combustible things, right? Like how do we measure, for example, like solar? You can't like combust the sunlight or anything, right? And so there have been a couple different methods that have come up to try and measure this. So I spoke last time in theory about how, you know, sunlight hits the atmosphere at about 340 watts per meter squared, and then it'll hit the ground. Um, but in order to understand the efficiency uh, of solar power, you you can't go around and measure the solar radiation at every sort of point, and how it changes over time too, right? As like clouds go overhead, you're going to get different amounts of solar radiation. And so the measurement of efficiency of a solar panel is much more difficult to take account of in practice. So there are a couple methods that have been come up with. One is the substitution method, where they say the primary energy of solar is simply equal to the solar electricity generation coming out of the solar panel divided by, say, the average efficiency of a fossil power plant. Um, and of course, this is really assumption driven, and depending, right, on what you consider the average efficiency of a fossil power plant can really change sort of how much energy we think is associated with solar power. And so be wary of numbers that are coming out of measured primary energy using like a substitution method, because it's going to depend a lot on the assumptions that you think about with efficiency that they're using as a substitution. Some other sources will use something called the direct equivalent method, where they just say, okay, the primary energy of the solar is equal to the secondary energy of the solar. So you're implicitly assuming that you get 100% conversion efficiency. So this is sort of on the other end of the spectrum, where you're going to be probably overestimating the energy content of the solar coming into your system. And in reality, it's probably going to be something that's going to be in between sort of your direct and substitution methods. For other non-combustibles, energy content, they use what's called the physical energy content, which is kind of a hybrid between the direct and substitution method. So it's the heat generated, any heat generated from a process for nuclear, solar thermal, and geothermal is considered to be the primary energy. So for those who don't know, solar thermal is different from solar photovoltaic. That is a power system that essentially has a bunch of mirrors that take in sunlight and aim it to a concentrated source. And what that does is boil some water to power a turbine. And so that's going to be different from the solar that I was talking about in the last slide, because in this way it's generating heat, which you can actually measure. So the heat generated by the fission reaction, so it's the nuclear chemical reaction that's happening to undergo fission of uranium generates heat, and you can measure that. And so that's what they're using as equivalent to the primary energy. So it's pretty similar to the case of fossil energy, except that you're not capturing the heat of combustion. You are capturing heat from a different sort of mechanism, and that's considered the physical energy. For hydropower, wind, tide, wave and sort of solar photovoltaic. The other types of renewables are also sort of using the direct equivalent method that we talked about in the last slide. Okay. So that sort of wraps up the discussion about how we're measuring energy content of different fuel sources in practice. And now we're going to think about when I go from a primary energy all the way, that pathway that it takes to go all the way to useful energy. How do we do that energy conversion? How do we account for efficiency? Energy, right, has to be converted from one form to another. The energy conversion from, say, chemical energy into heat energy or chemical energy into electrical energy, there's always a energy conversion efficiency associated with that. You can never have yes. All right, since this is a 2-hour class, are we going to have a 2-minute break halfway through? Yeah, I suppose we could. That'll probably help with your sanity as well as mine. I'm looking through for a good stopping point. So this may actually be a good place to have a quick break. So why don't we? Yeah, I'll do this from now on. It's a good suggestion. I think we kind of had a natural one last time because of that poll that didn't end up working. But let's convene for 5 minutes and we'll start up again. Yeah, so um, before we start again, I see a question. What do you mean by primary energy solar is equal to the secondary energy of solar? So there, the secondary energy is simply the electricity coming out of it. And in theory, you should be getting some losses because of conversion of the solar radiation into electricity. But because we don't actually know how much solar radiation is hitting the panels, essentially what they assume is that the radiation energy is equal to that conversion into the secondary energy of electricity. And so sometimes you may be measuring, uh, you're assuming essentially an efficiency conversion of 100% so that the primary energy content is equal to the secondary energy content. Yeah, that's exactly right. So if you wanted to emphasize the benefit of solar panel or solar power, oftentimes you would use direct equivalence over a substitution method. Generally, I think that you don't see that being too much of an issue these days because, when you talk about primary energy content and the measurement of solar content, um, with respect to something really specific, using a direct method or a substitution method, you're probably talking about a case study of the technology in like a really specific area. Um, Whereas I think a lot of the numbers that we use today still use sort of general averaged uh, solar radiation in a particular area. And even though that's going to fluctuate obviously over time and across the seasons, it gives a fairly good indication of the energy content. Um, and so you don't need to necessarily rely on either of these methods. Okay, so let's start again from our break. So energy conversion, we use this symbol to indicate essentially the efficiency of converting energy from one form to another. And as I was mentioning right before we started our break, is that you can't actually have a perfectly efficient system. If you did, that coefficient would just be equal to 1, but it's always less than 1. And therefore, the conversion losses are equal to 1 minus that efficiency coefficient. The energy conversion processes are governed by laws of physics and thermodynamics. And so if you think about the laws of thermodynamics, those often will give sort of upper bounds to the efficiency. So let's go to the first law of thermodynamics. So energy can't be energy can be changed from one form to another, but you can't it can't be created or destroyed. So the total amount of energy always remains constant. But there are some forms of energy that are more or less useful, and so just because the energy itself is conserved, the reason why you have that efficiency is because you're interested in a particular form of the energy, and that's what the efficiency is referring to in terms of the conversion from one form of energy into that energy that you're interested in. The change in internal energy of a system is equal to the heat added to the system minus the work being done by the system. And so if you had a system with like the fossil fuel, for example, and you're combusting it, you need to input some amount of energy first to start the combustion. And so that might be some kind of heat or energy input. And so whatever work that you're getting out of that system, you have to take away the energy input, and that'll tell you the delta in the energy of the system. So I also wanted to introduce a slightly different concept, which is outside of strictly sort of physics, but is common in the sort of world that we're operating in when we talk about energy conservation. So the first thing, conservation of energy, is exactly that, the first law of thermodynamics, where energy can't be created or destroyed, you're just converting it between different forms. Energy conservation, not to be confused with the first one, is more of a sustainability concept, so reduction in energy usage so that we're not wasting energy. So just keep that in mind, that when we talk about these two things, you're referring to pretty disparate topics, and so the context will matter when you're saying energy conservation or conservation of energy. So just have that clear in your mind when we're talking about this. Okay, so going back to efficiency. So when you think about going all the way from like a fossil fuel through electricity, through the end use into useful energy, it goes through a whole pathway of different systems and energy forms. And so the efficiency from the start all the way to the end is characterized by the what we call sort of the efficiency of the entire energy pathway. And that total efficiency can be measured by taking the product of each of your individual efficiencies. So I'll show a quick example of that in the next slide. So this is an example of a combustion fossil fuel power plant, specifically with coal. And what we can see here, let me use my annotation device, are multiple conversion processes. So the boiler, and we'll talk about exactly how these technologies work in later lectures. The boiler has an efficiency of 90%. Okay, and so what's happening there is you are combusting your fuel of coal through the boiler process here. And what happens is you combust the fuel, turns it into steam, and then sends it to the turbine. And so the amount of heat that's captured by the water that gets turned into steam is 90%. So this portion here is 90% efficient. You can then change, you send the steam through the turbine, which changes the chemical energy into mechanical energy. So the thermal energy into mechanical energy. You have both pressure and heat working in this turbine, and you convert some of that energy into movement. So the turbine will be spinning. And the amount of energy that you're actually able to capture there is 45%. And then lastly, the motion of the mechanical energy, which is going to be moving magnets in a generator, or you have a stator, essentially, that will transform mechanical energy into electrical energy. The efficiency of that process here is 95%. And if you are interested in the total efficiency of this whole system from beginning to end, it's a pretty simple process to figure that out. You just multiply the efficiencies, as we can see here. And so with a 90% efficient boiler, a 45% turbine, and a 95% efficient generator, your coal plant is going to be operating at 36% efficiency. So what that means is, if I think about the primary energy of coal, and right, that's something that we measure through the LHV or HHV. You know, say that has 100 units of, or 100, say, megajoules of the coal. The electrical energy, the electricity content of the the energy content of the electricity of that 100 megajoules is going to be equivalent to 36 megajoules. That's how much energy we're getting out of this conversion process. Your losses are at about 64%, mainly as heat, although some of it can be used for other things, right? So you could use it to heat the buildings, for example. Okay, and so this gives a relative efficiency level of a coal plant. So note that the strict definition of energy efficiency is defined as a dimensionless number. And so the units of the numerator are always the same as the units of the denominator, which is why you're working in these sort of like percentages. And so if oftentimes you're working from like fuels into electricity, those units are going to be different, and you're always going to have to do a conversion to figure out the efficiency. As I mentioned before, fossil fuels, for example, are often measured in terms of BTUs, MMBTUs, or in joules. So you're going to have megajoules or gigajoules. Whereas electricity is often measured in watt hours, so kilowatt hours, megawatt hours, gigawatt hours. And so when you do a calculation for efficiency, and we'll do an example of this, you always need to make sure that the units are the same before you calculate that percentage. Otherwise, your number is going to look really weird. You may also be familiar with this concept of efficacy, which is often a misnomer for efficiency. When we say something like fuel efficiency, how fuel efficient is your car? You might say, oh, you know, it's 25 or 30 miles per gallon, right? But miles per gallon is actually different units in your numerator and denominator. And so strictly speaking, we refer to that as efficacy. Yeah, I see a question. So is the transmission of energy to various places taken into account, or does this not contribute to major losses? Yeah, great question. So it actually is taken into account, but it depends on your endpoint, right? And so actually, if I were to continue this to going to the end use, you might have a transmission system going into your household. And this transmission may have another efficiency associated with it. So usually for a typical transmission system of average length, or it actually depends on how far away, but we typically estimate like a 97.5% efficiency. And so that's something that you could add on. So if I were interested in, so this to be a little bit more accurate, this would be electricity out at the power plant. But if I wanted electricity out at a household, you would want to take into account the transmission efficiency, and you would multiply 36 times, 97.5%. Okay, so hopefully that answers that question. Definitely, depending on where you decide to end your pathway, things like transmission would have to be taken into account.
There are questions about units. So.
Yes, yeah. I saw that. So going over the different units. Okay, so what I was saying here is that, and I'm actually going to show an example of this in a second. So hopefully that'll be clear. But to give a quick answer of this, you want efficiency. Say you have the output of electricity divided by input of coal. Usually electricity is measured in megawatt hours, and coal would be measured in BTU. So if I took the ratio of electricity in megawatt hours divided by the ratio of coal in BTU, that would not be the correct efficiency number. This needs to be converted to BTU, or this needs to be converted to megawatt hours. And then you do the division, and that'll give you the true efficiency. And again, I'll show an example of how to do this in a second. Efficacy is slightly different, and we actually talk about this still in terms of efficiency, but it'll be, again, something to keep clear in your mind as being different from this concept of efficiency. So when I say, oh, my car is 25 miles per gallon, so that's miles divided by gallon. We do refer to that as a term of efficiency, but for the definition that we're talking about here as a dimensionless number, I would more aptly call this an efficacy rather than an efficiency. And so hopefully that will make sense. I see a question. Are those constants for the conversion between units? Yes, they are. And I'll give a reference sheet actually in a couple slides that you can use as the constants that you would need to do conversion in between any of these conversions for forms of energy. Okay. There are, in addition to, so when I'm talking about efficacy, there are a couple different sort of efficacy or efficiency indicators. So thermodynamic, which is the output energy, input energy. This is really what I'm talking about with efficiency is this thermodynamic concept. And then the rest of these are, I'm gonna call them, I'm gonna say efficiency sort of from here on out, but know that sort of formally they're what I was referring to as efficacy. But so physical thermodynamic efficiency, where you have different units, so physical units versus input energy, these are useful. So these are like megajoules per kilogram or miles per gallon, that sort of thing. You can have economic thermodynamic energy, which is a cost efficiency. So how much it costs, or how much energy given a certain amount of money. And then an economic efficiency, which is sort of a dollars over dollars. And we won't deal with this too much for now, but it's something that may come up later, just so that you won't be confused. Okay. Oh, I see a question. So no matter what, efficacy and efficiency are unitless. No, so efficacy won't always be unitless. Those are things like the MPG that I was talking about. But efficiency, strictly speaking, for thermal efficiency, yes, it's always going to be unitless. So here I can actually show an example, right, of converting from a efficacy into a thermal efficiency. So the efficacy of this plant would be simply 100 kilograms over 11 gallons. So this would be, 9 point something. I'm just doing this off the top of my head. It was 9.09, right? 09 repeating. Kilograms of corn per gallon of ethanol. So that would be the efficacy, but the efficiency is to convert all of these things. Okay, so I can get the energy content of corn via heating values. So 18 megajoules per kilogram. And then I can also do the same thing for ethanol, 89 megajoules per gallon, and convert both of these into megajoules. And that will give me a thermal efficiency of 54%. So the conversion of the corn into ethanol reduces the energy content by 46%, which means that if in theory we could combust the corn or use the corn in a certain way that captures all of the efficiency or all of the energy output, then the energy that we can get out of the ethanol is going to be lower because the conversion process actually loses some energy. Similarly, you can have an efficiency of like a pipeline, or as someone had mentioned in chat before, of transmission, right? And so even here, it's not necessarily talking about energy efficiency and conversion of one form to another. It could be the transport of energy from one end to another. And so in this pipeline, we can actually say efficiency and not efficacy because you're using the same units for the input and the output. So if I took 100 gallons of the input and I combusted it all, and then I took what I got out of the output, you're only getting 95% of the energy because you're losing some through like leakage. And so we consider this pipeline to be 95% efficient without changing the form of energy. And then we can do even for electricity into useful energy. One of the ways you can do this is for example, for an incandescent light bulb, I could measure the lumens and wattage of the useful energy of the actual light that I need to use for my useful energy, but I know that it takes some amount of electricity energy to make that light. And so the conversion of the light bulb from the electricity input, it needs 60 watts, but it's only providing me with 3 watts of light energy. It's only 6%. Okay, so then there's a question here, where does the other wattage go? Good question. So this example is definitely an example of an incandescent light bulb. And so if any of you guys remember, prior to maybe around 2013, they were a lot more common. And those light bulbs get really hot, right? And so the heat energy is not the useful stuff that we want. We want the light, but that's the loss, is the electricity into heat energy that we're not using. So the efficiency of the useful energy is going to be 6%, where most of the rest of that stuff is lost as heat. This is a pretty common type of figure that you'll see, or some form of this figure, which gives you a nice sort of sense of what the losses look like from my energy source, primary fuel, all the way to the end final services. So this might be something like coal or natural gas. You have to you do some refinement and you convert it into electricity. And so you're going to get a whole bunch of losses through heat and through transmission and distribution losses, conversion losses, and the amount of useful energy and its conversion to final services. You'll see that in each step of that pathway, you're decreasing the amount of energy that's available for whatever you need at the end, and each of those decreases are associated with an efficiency decrease. Yeah, actually, I'm gonna skip this slide because actually it's basically saying the same thing with some numbers. In each step, you're doing some conversions, and you're losing some of the total energy. This is a sort of nice little example of a particular use of a light bulb, where you're going all the way from the starting life cycle of gas or coal, generation, transmission, all the way down to the useful light at the end, right? And what we can see here is that you start with about 320 units of energy. It's just a generic form of energy. We're all keeping them all in the same units. And so to produce 1 unit of useful light, you need 320 units of starting energy. Okay, so in terms of the electricity, most of the losses are coming from the generation when you're combusting the fuel. And then you lose a little bit in transmission, you lose a little bit in distribution, some in wiring. And then actually, this is a particularly big example of a bad or low efficient end use technology. So this light converts 98% of that electricity to heat, and about 1% of it into useful light. So the bulk of the losses in the system are actually happening from your light bulb and not from the power plant, right? The losses are quite a bit bigger. So that actually begs a sort of important question from a policy and technology development perspective. So if I had the choice to like improve one part of that pathway, to improve the efficiency, any sort of like energy conversion step, where does it make the most sense to improve? Well, it's not always clear. There isn't like one sort of right answer. There are benefits to doing one versus the other. So improvements in final or service efficiency. So that might be something. Yeah, I see this actually a question: which part do we usually improve to reduce the loss? So that's actually exactly what this slide is addressing here. So I could improve the final service efficiency, which would be like getting a more efficient light bulb, right? And actually, if you think about what that means back in this chart, if I need less energy here, that essentially improves the efficiency of every step before it. And I'll show what that looks like in a second. So every upstream stage means that if I improve the light bulb, you need less mining and oil extraction, you need less power plants, you need fewer pipelines and transmission systems. All those energy losses get absorbed. On the other hand, if you improve a primary or secondary efficiency, so this would be something like improving the power plant efficiency, this can be more centrally implemented. So when we talk about economics, which we'll cover in a future lecture, we'll find that energy companies or centralized corporations are typically more rational actors than individual consumers. So even if like improving a light bulb helps a lot more in terms of the actual energy efficiency because you reduce energy at every step, it may be easier to upgrade a power plant than to get everyone to buy like a new light bulb, right? And so let's take a look at the effect of improvements. So these two figures are actually exactly the same as before, except we've changed a certain parameter. So yeah. Okay, so I see a question: if the surrounding temperature is lower, will it produce more energy? Okay, that's let's see, it depends on the sort of energy conversion process that you're talking about. I think what you're thinking of is like a difference in temperature gradients for improving or decreasing efficiencies. And I guess we're probably not going to talk so much about that specifically, other than to say that yes, the conditions in which certain energy conversion processes are happening will change the efficiency. That's for sure. But we're not going to talk about how that changes. Typically, you know, either we're going to provide efficiency numbers. You're not going to have to like calculate them yourself based off of like conditions, and those ones typically are in conditions that we expect to happen. Okay, so going back to this example, so these are two types of efficiency improvements. So the top one is the latter one I was talking about in the slide, where you have a more centralized, where you're improving the primary to secondary efficiency. So this is, if I change the power plant from 35% efficient to 50% efficient, so then the losses here are smaller, which means you get to start with less energy. So in the previous slide, if I jump back really quick, we start with 320 to get one useful unit at the end. But here, if I improve the power plant, I only need to use 224 compared to that 300 number, right? And you can do the same efficiencies for everything else and get to that same useful light energy. Okay, let's suppose now we improve the light bulb instead of the power plant from 2% to 10%. What ends up happening, as I was mentioning before, is that it affects the energy demand of every upstream step. And so going from 2% to 10% efficiency at the end use drops our primary energy required from 320 down to 64. So there's an 80% reduction in the primary energy, which is equivalent sort of here, right, to the energy reduction that you need here, because it flows through every previous step. Yeah, and so the difference between upgrading your power plant versus upgrading your useful energy service efficiency at the end can be pretty different, right? And again, this kind of goes back to that idea of like, oh, we should just make everyone improve their light bulbs. But at the end of the day, it's oftentimes harder to get consumers to change their behavior or to adopt a new technology. Think of like electric cars, for example, than it is to make a centralized change, right? So, or to make like, for the electric car analogy, it would be like having the automakers all produce just more fuel efficient vehicles, as opposed to forcing consumers to buy electric vehicles. Yeah, so there's a challenge between the larger benefits that you're getting from end use efficiency improvements versus the easier time it is to make those improvements in a more centralized fashion. Okay, so the last thing that I'll talk about before going to our examples, energy quality. So what's the difference between 1 megajoule of electricity versus 1 megajoule of like biomass if you had like wood? Well, actually, if you think about that, like the energy content of the wood, we're able to extract less work out of that compared to getting energy out of like electricity, right? And so even though two different materials can have the same amount of energy, there's a different concept that refers to the quality of the energy or how useful that energy can be to us. Okay, wait, sorry, before I go there, I see a question. Which number should we look at if we want to know the total efficiency? So the total efficiency would be, I don't think I have it up here. You would essentially multiply each of these efficiencies. So 50% times 5% times 5% times 1%. times 98% times 50%. That'll give you the total efficiency. Okay, so exergy is the maximum amount of work that can be derived from a system. And so this is the measure that we use to have energy quality. Okay, and there are like hierarchies of this. So energy is always conserved, but exergy is destroyed. And we generally consider electricity and mechanical energy to have a lot more exergy than chemical, which has more exergy than heat energy, right? So when we think about these sort of diagrams, all of that useful exergy, you can compare an energy diagram versus an exergy diagram, and any of these losses are coming from like and heat and that sort of thing. And anytime you convert energy form from one to another, you're losing some exergy to either like chemical or heat. This is a diagram that shows sort of relative amounts of exergy for different types of fuels or different sources of energy. I'm going to quickly skip through this so we can get to at least one example of energy conversion. And actually, I'm probably not going to be able to go through all of the examples, but we'll actually pick up where I left off in the next lecture to do the very final example. But so these are just some reference slides for folks, things to keep in mind. And this is the reference sheet that I'm gonna be talking about, or I'm gonna be using for some of the examples, and that you can refer to in future homeworks or even projects. Okay. So how much electrical energy can be derived from 1 ton of coal? So the way in which we do these types of problems is called dimensional analysis. I'm sure if some of you guys have done chemistry before, you'll be familiar with this, but we'll just walk through these examples and talk through them so that we can understand how to do it and what the dimensional analysis entails. So the first thing that you want to do is to think carefully about your inputs versus outputs. So we're starting with 1 ton of coal, which is going to be the starting point on the left-hand side, and we want to get to electrical energy. So electricity, again, to harp on this, is measured in terms of watt hours. And so I'm going to try and convert my 1 ton of coal into ultimately some unit of megawatt hours. So we'll go ahead and do this. So 1 ton of coal, which is our starting point, you multiply by 28 gigajoules per ton. So this particular conversion is in the reference sheet. I'll just jump back real quick. So that's right over here. The energy content of coal is 28 gigajoules per ton. The other thing that we'll need to know is its conversion to electricity. So that's these two here, coal to electricity, 35% and 45%. But you also remember that you have to do, anytime you do a conversion efficiency, it has to be in the same units. So we need to go from gigajoules into megawatt hours or kilowatt hours. So that's down here, this conversion factor, 277.8 kilowatt hours per gigajoule. So if we use all of those pieces of information, I can do this, multiply by 277.8 kilowatt hours per gigajoule, and then multiply by the efficiency. So this is 35 kilowatt hours per 100 kilowatt hours. And what this means is that you get 35 kilowatt hours of electricity for 100 kilowatt hours of coal. Okay, and so this is from the steam plant efficiency. And this would be the same as multiplying it by 35% or 0.35. The reason why I'm specifically writing this out is so that you can remember that when you do the efficiency calculation, it has to be unitless and in the same units as what you want in the end. So this is equal to 2,722.4 kilowatt hours. Okay, I see a question. How do you know to use the steam plant efficiency instead of the other one? Well, actually, I was going to write out, so the steam plant efficiency is equal to 2.7, approximately equal to 2.7 megawatt hours. And then the gasifier one, I'm just going to write out for both, is about 3.5 megawatt hours. So the question was, which number do I use here, the 35% or the 45%? So you will either specify yourself that for for one process it's this, and for another process it's this. It's part of the assumptions that you're making. So here I'm actually just kind of commenting for both. Let me get rid of that. Notice, let's see. Actually, I'm gonna talk about this next time because we don't have time to get through the rest of the examples. But for this final answer, I'm reporting it with just 2 units. That'll be important to consider. It's called significant digits, significant figures. I'm sure a lot of you guys have heard of that, but it's something to keep in mind. Even a lot of my grad students forget about this. And we'll talk next time at the beginning why that's important and how to actually take that into account. But for this example, the dimensional analysis, the way that I know how to structure this problem is, as I do the conversions, you want to keep everything canceling out in terms of units in the numerator and denominator. And that'll keep you sort of safe as a way of keeping track of your flow through structuring the equation. Okay, so I'm out of time today, and I don't want to keep us any longer. If you have any questions about this, you can start one in the Canvas discussion. Otherwise, I'm going to go through the rest of the examples at the beginning of next class so that we have a clear idea in our mind about how to do this, and so that folks aren't confused. Okay, in the last minute or so, any questions? Okay, well, barring none that are popping up in chat right now, thanks everyone. And I will see you guys all on Monday at noon.
Okay, see you on.
Bye.
There's a question, sorry.